Data is at the heart of modern medicine, driving breakthroughs in patient care, predictive modeling, personalized medicine, and healthcare AI. By providing access to diverse and comprehensive health data, Mimic3 has become a cornerstone for advancing our understanding of critical care and driving innovation in medical research. The Medical Information Mart for Intensive Care 3, or Mimic3, is a freely accessible critical care database containing de-identified health data from over 40,000 patients admitted to the critical care units of the Beth Israel Deaconess Medical Center in Boston between 2001 and 2012. Published in 2016, it was the first database to span over a decade of diverse data, significantly advancing research based on public intensive care datasets. In this introduction to Mimic3, we'll get an overview of the database's structure, the types of included data, and patient demographics. By examining the data firsthand, we'll uncover the importance of context in clinical datasets. Finally, we'll follow a patient's journey through the hospital, showcasing how this data can drive improvements in healthcare. Overview. The current version 1.4 of the Mimic3 database is hosted by PhysioNet and consists of 3 primary tables: patients, admissions, and ICU stays, linked by unique identifiers and further connected to 23 additional tables. Since one patient can have multiple hospital or ICU admissions, the tables follow a one-to-many relationship. The data in Mimic3 includes both structured formats, such as charted bedside measurements, and unstructured formats like clinical notes or discharge summaries. Most tables include timestamps, enabling time series analyses. Additionally, the database provides dictionary tables to map item IDs or ICD-9 codes to their corresponding terminology. Mimic3 contains data from 46,476 distinct patients, including 7,879 neonates, and covers over 61,532 ICU admissions. A slight majority of adult ICU patients are male, with a median age of 65.8 years. The intrahospital mortality rate is 11.5%, and most patients self-identified as white and were publicly insured. Examining the data. While technically public, access to Mimic3 is restricted to users who agree to comply with ethical guidelines for human subject research. To gain access, you must complete a certified training course on human subjects research, e.g., city data or specimens-only research, submit personal details for credentialing on PhysioNet, and sign a Credentialed Data Use Agreement (DUA). Although the process may initially seem complex, it is relatively straightforward. Mimic's website provides clear instructions on the application process and offers guidance on setting up access once approved. Overall, Mimic3's documentation is well written and accessible. Why this documentation is important, and why you should read it, will become clear in the next minutes. In this histogram, I've plotted the number of heart rate measurements taken from ICU patients. Those with a medical background might notice something unusual. While a peak between 60 and 80 bpm is expected, the smaller peak around 150 to 160 bpm seems odd. Looking at the documentation, we learn that the ICU data comes from 2 systems, Philips CareView and IMSoft MetaVision. Plotting heart rate distributions by system reveals that the unusual peak originates from the CareView system. Was this a system defect? Recall that the database includes data from neonates. Could they be the cause of this second peak? Examining the age distribution of patients linked to each system confirms this. CareView includes data from over 7,000 neonates. Revisiting the heart rate histogram and separating data for adults and neonates clearly shows that neonates are responsible for the second peak. To further illustrate, this figure shows the heart rate plotted against the patient age. But what's this, patients over 300 years old? This is due to de-identification measures in line with the Health Insurance Portability and Accountability Act. In addition to removing identifiers like names and addresses, dates were randomly shifted in a manner to preserve intervals while obscuring characteristics like birth and death dates. Patients aged 89 or older were recoded as over 300 years old. In the previous plots, I excluded these patients for clarity. As you can see, understanding the context and reviewing the documentation beforehand is crucial to avoid any unexpected surprises. A patient's journey. In this chapter, we'll follow the trajectory of a specific patient. Let's call her Jane, an active woman in her mid-60s who recently returned from a trip. Jane has a history of hypertension, type 2 diabetes, and hypercholesterolemia. On the day of admission, she presented with 3 weeks of worsening shortness of breath during activity, swollen legs, and a week of difficulty swallowing. The following plot shows a timeline of Jane's 2 hospital admissions. We can trace her stays, observe the decline in her vital signs, systolic, diastolic, and mean blood pressure, as well as heart rate, and, sadly, her date of death. Jane was admitted twice due to congestive heart failure, a life-threatening condition in which the heart cannot pump enough blood to meet the body's needs. During her second stay, her vitals showed an increased heart rate alongside low blood pressure. For reference, normal blood pressure is around 120 to 80 millimeters of mercury. Thanks to the richness of data in MIMIC-3, we can zoom in on her second ICU stay. About 20 hours after admission, Jane's heart rate and blood pressure briefly dropped, and the frequency of measurements increased. At the same time, the amount of fluid and medication she received rose sharply. From the medication log, we see that several drugs were introduced at this point. Additionally, invasive blood pressure monitoring was set up, explaining the increased measurement frequency. These interventions indicate a worsening condition. 4 to 5 hours later, Jane received fentanyl and midazolam, drugs commonly used for sedation. Her Glasgow Coma Scale score confirms that she remained comatose until her death, 63 hours after ICU admission. Utilization in healthcare. Instead of focusing on a single patient, we can also analyze a cohort of patients. This highlights one of MIMIC-3's key applications, predictive modeling and mortality prediction in healthcare. For example, Lee et al. Used MIMIC-3 to develop a prediction model for in-hospital mortality among heart failure patients. They included 1,177 patients and created a nomogram as a bedside tool for quickly identifying critical conditions. Although Jane did not fulfill the inclusion criteria of the study, her data contains all the parameters needed to apply the nomogram. Using the first complete set of measurements during her ICU stay, coinciding with the worsening of her condition, we calculate her in-hospital mortality risk. After recording and scoring the parameters, we find her predicted risk exceeds 90%, emphasizing the severity of her condition. This information could help doctors make critical clinical decisions regarding medications, interventions, or other life support measures. Beyond predictive modeling and clinical decision support systems, MIMIC-3 has been instrumental in diverse clinical research applications, including outcome analysis, epidemiological studies, and insights into patient safety dynamics, such as pharmacovigilance. It has also been widely utilized in education and in the research and benchmarking of machine learning models and AI in healthcare. While MIMIC-3 has inspired the development of other public medical databases, it has notable limitations. As a single-center database, its generalizability is restricted, with social and economic characteristics reflecting the Boston area, which may not be representative of other regions or countries. The dataset also exhibits feature imbalances, such as the majority of patients being white and publicly insured, which could introduce biases into predictive models. Moreover, less common diagnoses and procedures, along with inherent biases in the original data, present challenges for broader applicability. Additional hurdles include privacy considerations, the complexities of de-identification and processing, particularly for unstructured clinical notes, and difficulties in managing missing or incomplete data and addressing temporal variability within the dataset. If you'd like to dive deeper into MIMIC-3, check out the video description for links and references, including the MIMIC-3 paper, website, the mortality prediction study, and the GitHub notebooks used to generate some of the visualizations. In this introduction to MIMIC-3, we covered its structure and content, the importance of context when analyzing medical data, and the depth and versatility of its information. MIMIC-3 has been a pivotal resource, driving advancements in healthcare AI research, enhancing education, and offering valuable clinical insights, particularly in patient safety and quality of care. In 2023, its successor, MIMIC-4, a freely accessible electronic health record dataset, was published, continuing this legacy.